In the previous lesson, we introduced electromagnetic theory, distinguished scalar from vector fields, and previewed the three coordinate systems we will use. Now let's dive into the first one, the Cartesian coordinate system. We'll define the axes, the unit vectors, and the three differential elements that appear everywhere in EM theory: line, surface, and volume. The Cartesian coordinate system uses three mutually perpendicular axes: x, y, and z. At any point in space, we define three unit vectors: Ex pointing in the x direction, Ey in the y direction, and Ez in the z direction. Each has a magnitude of exactly 1. These unit vectors are orthogonal, meaning the dot product of any two different ones is 0. And they obey the right-hand rule. Ex cross Ey gives Ez, Ey cross Ez gives Ex, and Ez cross Ex gives Ey. This cyclic relationship is fundamental. Any point P in space is specified by three coordinates: x0, y0, and z0. The position vector r points from the origin to P and is written as r equals x0ex plus y0ey plus z0ez. For example, the point P at 3, 2, 4 has the position vector r equals 3ex plus 2ey plus 4ez. The magnitude of r gives us the distance from the origin, the square root of x squared plus y squared plus z squared. The differential line element dl represents an infinitesimal displacement in space. In Cartesian coordinates, it is dl equals dxex plus dyey plus dzez. When we move only along the x-axis, dl simplifies to dxex. Along the y-axis, dyey. Along the z-axis, dzez. The magnitude of dl is the square root of dx squared plus dy squared plus dz squared. We will use dl extensively when computing line integrals of fields. The differential surface element ds represents an infinitesimal patch of area with a direction given by the outward normal. In the xy plane, the normal points in the z direction, so ds equals dx dyez. In the xz plane, the normal is in the y direction, ds equals dx dz ey. In the yz plane, the normal is in the x direction, ds equals dy dz ex. To remember the sign, use the right-hand rule. Curl your fingers from the first axis to the second, and your thumb points in the direction of the normal. This gives us the positive orientation. The differential volume element is the simplest of the three. It is a scalar quantity. dv equals dx times dy times dz. This represents the volume of an infinitesimal rectangular box. Unlike dl and ds, the volume element has no direction. We use it whenever we integrate a scalar field over a volume, for example, when computing total charge from a charge density. Let's review. In the Cartesian coordinate system, the position vector is r equals xex plus yey plus zez. The line element is dl equals dxex plus dyey plus dzez. The surface element ds depends on which plane we are on, and the right-hand rule determines its sign. The volume element is simply dv equals dx dy dz. In the next lesson, we move to cylindrical coordinates, where the geometry becomes circular.